To start with, if you are entering a clumsy room, and if I just say to find something, it would be really tough. But if I say to search for something you can play music with, giving the context to play music with, it would be easier to find a guitar there. So context can be helpful in making things easier, understandable, and finding easy. Can this be useful in even in spiking neural networks? Recently, context-based spiking neural networks were proposed, which were showing that having two streams of information, context and input, can give on-par accuracy with most of the networks using much lesser number of parameters. This was happening because of taking inspiration from neocortical pyramidal neurons, which is multi-compartment setup, which has an apical tuft and then basal dendrites, which uses two independent streams of information, top-down information and bottom-up. And bottom-up basal dendrite depends on both top-down information and bottom-up information. This is how it works. When there is some input and no context input, then there is no increase in membrane potential at somatic compartment. But when there is some context and also a somatic input, then there is increase in membrane potential. Both are acting as a leaky integrator compartments, but still both the somatic compartment fires only when it reaches a certain membrane potential. This can be useful in exploring temporal dynamics in selecting particular neurons for a particular class. And this is done through attenuation and amplification of stimuli input based on the context or apical membrane potential. So now that it's working, we want to make an hardware of it. If we no-brainer make an hardware directly implementing the equation, then there would be a lot of multipliers and adders, accumulators, and it's not really hardware friendly. And if you start with some n-bit input, and if we don't want to cross overflow, we require 8-bit finally, because it is pipeline, 8 n-bit. So first idea was to remove the exponential leakage and do a linear leakage, and find the parameters which would be helpful in certain range. And we were able to do that. And we modified the equation with the current value or apical compartment or somatic compartment will be decayed with a constant voltage. It resets whenever it is 0, or somatic compartment resets when it reaches a certain threshold. And this was done on mostly spike inputs. So spike inputs here distally are 0 or 1. So instead of multiplication, we were able to do the logical and few pipelined addition to get the spike accumulated output. This is a single neuron model, which neural model digital design, the proposed quantized context-based LIF neuron. And we were not freezing any of the leakage because heterogeneity in the leakage values was helping the network. Then we made a complete architecture of this recurrent spiking neural network hidden layer, and we were able to see that it requires certain inputs and outputs. Now that we made an architecture, we need to decide the number of bits required to operate it. Assuming that a network which could solve in devious gesture classification, it requires at least 200 inputs and self-connecting 200 recurrent connections, which will have 400 inputs. And if we are having 400 inputs, and if we have at least 8-bit weights, then it would cause me to start my operation with 64 bits and end with 64 cross 64 multiplier and 128-bit, which would be very, very expensive. Thanks to sparsity, the events of somatic input and apical input were really sparse, and we were able to operate at much lower bit widths. And also we did the hardware we are doing is inference. So we tried to quantize the weights in a particular range. Then we did quantized aware training for neuron states and also neuron weights with the linear leakage and the quantized CLF. We were seeing that even at full precision, when compared to the full precision CLIF neuron-based network, only 0.5% accuracy was decaying. Still, we tried to do it at 8-bit and 4 bits, as we thought 90% was also a decent mark. We built we tried to complete a pipeline till the layout for single neuron and two multiple neurons. And we did further analysis on multiple neuron, one hidden layer. So we tried to do estimate of which clock frequency would be better, and we tried to do it on different clock frequencies and identified that at a higher clock frequency, it takes lesser energy, and at lower frequency, we know it takes more slack. So we decided it would be at something like 100 megahertz. The area for this 10 QCLF neurons will be like 0.125 into 125 millimeters square. Later, we wanted to check the scalability of the design. So we tried to move it from a 10 neuron network to 200 neuron network, such that whole devious gesture classification can happen there. And we were able to see that there was a sublinear increase in power consumption and sublinear increase in area. We identified that accumulator, the spike weighting accumulator, is taking the most of the area and power. Later, another aspect of scalability is decreasing the precision. We saw that moving from 8-bit to 4-bit on 200 QLF neurons, we can do energy reduction more than 50%, which is not so good. And we are getting greater slack. So if we want to do something at high speed, then we can operate on much more lower bits. We tried to, this was the first implementation of a context-based recurrent spiking network and this neural model. There was no literature to exactly compare apple to apple, but we were seeing that also already having a complex neuron model, still the energy per spike operation is on par with most other networks. And with the careful hardware software co-design was really helping the network to optimize. There are few limitations of the work which we saw that the accumulator was taking most of the space. If we can move that into a sparse accumulator systolic array or a crossbar, then maybe we'll save a lot of energy, but there would be a few more problems coming. And other thing is that this was simulated, not fabricated, at 45 nanometer open source PDK. And other thing is that this is not asynchronous. Everything is synchronous. Even the two compartments in the neuron model needs to be synchronous in the current design, which is not following the real neuromorphic. I would like to thank all my co-authors. This wasn't a project which was outcome from one of my course project, which I did in fall 2023, led by Professor Kim. And I would like to thank my discussions with multiple people. I'd be happy to discuss if there are any questions, and you can also reach out to me.